All good now.
We're recording. Okay. Now, to start with, thank you, Balvin, for that introduction, and in particular for the invitation to talk to the Information Physics Institute about Emergent Information Theory. As you said in the introduction, a new theory which I've been developing over the last couple of years. So a great opportunity to be able to talk to people who are interested. So also thanks to all of you for joining in this talk, and hopefully my talk itself is about 35-40 minutes, so hopefully at the end of that we have time for some discussion. What to expect? I would like to start off with a quick introduction of myself, not out of vanity so much as in explaining how I came to this theory in the first place. I think that would be helpful. Then a quick elevator pitch of the theory itself, just to give you a kind of a context of where I'm heading to, but that's a high over kind of explanation. And then going into a deeper look into emergent information theory, hopefully to convince you that there's something in it. To be prepared, there's no maths or algebra in this whole thing, because basically it's a conceptual story that I want to bring across. So it's more pictures than maths. And as I say, hopefully at the end we can have a discussion about the strengths and weaknesses. Perhaps you can tell me why I'm totally wrong, or at least how I can improve the theory moving forwards. So who am I? Quick bio. This is me back in 1981 with friends from university, University of York, where I studied. And I chose biology as a study because I was basically fascinated by the complexity of living organisms and learned a lot about the mechanics, in any case, of biological systems at university. For instance, the way that information in the genome is transcribed to create proteins. And the implicit story there was kind of that now we've explained genetics, we knew and had an explanation for the multicellular organism. And at the time that I found that difficult to accept, let's say that. Because if you think about it, we have 23 chromosomes in the human genome with 20,000 genes. And if you look at the degrees of the way in which a human body is constructed, then it has far more information necessary to define it than could possibly be contained in those 20,000 genes. So after that, after I left university, I moved to Holland, as Melvin said. I took up a career in IT. I didn't actually follow up with biology in that respect, but on the train, which you can see here, going through the Dutch landscape, on the way to work every morning, on the way back, I kept reading about the developments, because in the years after I left university, there were significant advances made in complexity theory, emergence, self-organization, as explanations for the formation and function of multicellular organisms, which came a lot closer to what I was looking for in understanding that complexity. Where it really came to a head for me was when I started reading about the connectome, which has been described as the most complex structure in the universe. And when you look at that complexity from the cellular, the microscopic level, all the way up to microscopic level, it becomes eminently clear that there's absolutely no way that could be defined by the quantity of information that is available in the genome. That was the physical side of things. Shortly afterwards, I bumped into Chalmers and his hard problem of consciousness, in which he says that, materialism is fine. So even if we do completely understand the structure and function of the human brain, for instance, that there will still be something missing. There's still something else to account for, which cannot be accounted for purely on the basis of the neurons, the synapses, the neurotransmitters, or whatever, which we have come to know there. And to make the hard problem even harder, when you look into that, you find out that throughout the course of human history, there are a great many people who have tried to solve this problem, the mind-body problem, in all sorts of different ways, and that to this day there is no consensus, which yeah, is a remarkable situation compared with other sciences where there's a really solid foundation which everybody can build upon. In this case, there are completely conflicting views on the relationship between the mind and the body from religious, philosophical, neuroscientific points of view. Whereas when push comes to shove, there is only one brain, there is only one mind, there must be only one explanation. So thinking about this, one day when I was on my way to work, I was coming out of this tunnel at Amsterdam Zuid, and I had an idea. What if I could combine what I had been reading and learning about emergence with what in my day job, basically, I was finding out about information in IT. And at that time, it was very much just a very abstract idea, but in the years that followed on the train on the way to work, rather than reading, I took to writing. And that led to the production of this book, getting on for 600 pages, which I printed a couple of copies of this to share with family and friends, and then thought a bit of a shame of all that work if it didn't get further into society. So I contacted a number of publishers, and needless to say, most of them said thanks, but no thanks. But one of them, Routledge, said, "We think it's interesting, but surely you understand that until you've published in a peer-reviewed journal, then we cannot take the risk of publishing a book. So do that first." So what I then did for a couple of years, 4 years about, was write articles and submit them for publication in academic journals and get them refused and refused and refused until January 2020, Interdisciplinary Science Reviews accepted the publication of one of my articles that I'd entered. Shortly after that, it was picked up for a reviewer article in Research Outreach. And from that, I got an invitation to do a presentation at the International Society for the Study of Information, their online meeting in 2021. And that led obviously to an article in the Proceedings. And from that, there was also a spin-off publication in New Explorations. With this under my arm, I went back to Routledge and I said, "I don't know if you remember me, but a couple of years ago, I contacted you and you said, get published and we might consider your book." And they were open to the suggestions, so they gave me a contract. And the last couple of years, I've been writing existing in the information dimension, which is actually a complete rewrite of the original book, because in the intervening years, I found out that, in fact, my ideas on the subject had changed quite considerably. Melvin has been so kind as to publish this, as to put this on the website, a link to this book. So if this presentation whets your appetite to know more, to hear the full story, then try to get your hands on one of these books. But enough of the sales talk. Now the elevator pitch. So this 2 + 2 is something. What is that? Emergence and information. To understand this completely, we have to be very clear about the kind of emergence and the kind of information that I'm talking about, because both of these terms are used in very different ways. And if you have a different idea of what I'm meaning by emergence and information, then basically the theory doesn't work. The emergence I'm talking about here is comparable to that which we see in the whole of physical reality, that starting from quarks, we have combinations of components which build up through multiple layers of organization to form ultimately matter, humans, stars, galaxies, all the rest of it. And at each level, there are new properties which do not exist in the underlying levels. In this specific example, if you see that as a drop of water, the wetness of water obviously does not exist in the molecule H2O or in the atoms that underlie it. So that's the kind of simple emergence that I'm talking about. A construction from component parts in which each level has its own properties. The information I'm talking about, particularly talking to you guys for who it's obviously a very important topic, is slightly more difficult to define. The easiest way I find of doing that is to couple it to the bit in the computer and the binary value which is associated with it. It's that kind of information, which is, as I say, very different to a number of other uses of the word information that you can have. If I combine these two, what happens if a number of these binary values get together, are combined in some way to create something at a higher level of organization, which has properties which do not exist in the binary value itself? Now, this in itself is a bit of a no-brainer, not at all exciting or radical in any way, because anybody who knows computers knows that this is actually how they work, that we do combine binary values to form bytes, and a number of layers of organization are involved before you get to the level of the programs which have the function which we require of them. And if you visualize this, you can see that it actually looks very similar to the hierarchical organization of physical matter, with the very big difference that while the binary values are associated with physical states, everything which is built from them is actually not detectable. And the reason why it's not detectable is because it's not made of matter or energy, it's made of information. And perhaps more radically, it doesn't actually exist in physical space. These are things which I will come back to later. It's surprising to us to think about computers that way, because a computer for us is a physical thing, it's a machine which you deal with. It's built up of component parts in much the same way that a car is built of component parts, with a very big difference that when that car rolls off the production line, all you need to do is put petrol in the tank and it'll drive away. Whereas a computer, when it comes off the production line, can do nothing whatsoever. Because in order to operate, it requires not just hardware, but also software. And if you look at these two component parts which are required to get functionality out of a computer, you see that it involves completely different skills. On the left-hand side, we have a hardware engineer. He has to know everything about electronics, doesn't really need to know anything about computer programming at all. On the right-hand side, we have a software engineer. He needs to know everything about the logic of programming, but doesn't actually need to know anything about the architecture of the hardware on which it's running. So we see here a distinction, in my view, between a physical realm, and that's where the computer that we look at and we operate with exists, and the information dimension in which the function of this computer actually exists. And in my view, the computer that we see is actually no more and no less than an interface between the two. I say no less because it's absolutely essential in order to gain access to that information dimension that we have a keyboard that we can type on and a screen that we can see the results of. But there are separate worlds of a very separate nature. And that is what you see here, that there is, on both ends, there is that, if you like, emergent functionality, that on the physical side, we have component parts which are brought together in order to create a functional computer. And on the information dimension side, we have those various levels of programming which are necessary to create, for instance, the PowerPoint presentation that I'm using now. Interconnected worlds. And what struck me, going back to my biological origins, was that this is actually very similar to what we see in brains, that here also we have a physical realm, we have neurons, we have synapses, we have neurotransmitters. And on the other side, we have the functions which the brain exhibits, often exhibited in behavior, but also in, for instance, phenomenal consciousness. And my conclusion was that, in fact, every evolved biological and designed technological system which has an informational function based on some kind of physical substrate has this nature. It is actually an interface between the physical world in which we build these things or in which they grow, and the informational world in which they perform their functions. That's the elevator. So now I need to go back to the basics to explain how that would actually work. And to do so, going back to the computer, you see here two physical objects, a white circle and a black circle. They have properties which we can objectively observe, measure, the size of the circle, whatever else. And if these were bits in a computer, they could be associated with a binary 0 and a binary 1. In this case, what's important is that while we can detect the physical properties, we cannot actually detect the binary values. And that may seem a little bit odd in the first instance to say that, but if you think about it, if I take that away, there's no way that you can actually tell me which of these is associated with 1 and which is associated with 0, because just as well as having 1 with black and 0 with white, we could reverse it, or we could replace the circles with something else like a magnetic orientation or whatever. All that makes no difference as long as the system knows how to use which state. And what's important in computers is that, in fact, the detectable physical properties are not the basis for the functionality of the computer itself, which we require from it. The functionality is in those non-detectable information entities which are associated with them. At this stage, you could say, so what? A single bit associated with a single binary value, you could think of it as just a sort of a property. Okay, you can't measure it, but it's not very radical. But binary values are not unused to us whatsoever. In order to get function out of a computer, we need to combine those, as we've seen in the previous slide, to form higher level phenomena. And that starts with, in general, with an 8-bit byte. So we have a sequence of 8-bit states, physical states, which are associated with a sequence of binary numbers. And we combine these in a particular way to form a byte. But again here, and even more so than in the case of the binary values, what you can see is there is actually no way, just knowing that bit sequence, what the decimal value would be associated with this byte. To give an example of how that is kind of arbitrary and non-detectable, if we reverse the black and the white 1-0 association, then we get the difference between the top and the bottom examples here. And we can also read from left to right or from right to left, and that will also give us 4 different decimal values associated with exactly the same bit sequence. And it's the decimal values which are, of course, what we need in order to build further the function of the computer. To make things even more interesting, what struck me was that in the case of the function of a computer, physical proximity is not the same as functional proximity. On a usual computer disk in the old-fashioned world, where we had actually computer disks, we actually stored things in segments all around, spread around the disk, and that was often fragmented. So what you notice in this situation is that while bits which are next to each other on the disk are physical neighbors, they are not necessarily informational neighbors. On the other hand, functionally proximal bits may well be spread on completely different areas of the disk. And following on from this, what you can see is that the topology of the information which is stored on a computer disk is completely different to that of the physical medium. The physical medium is basically linear. You just need an address to find a particular bit or on a disk, whereas that can actually support something with a very more complex and different structure, such as a relational database in this case. So here again, you see a distinction between the physical substrate and the information which is created on that basis of that substrate. So concluding this, what we can see is that functional emergence in computers is based on sequentially stacked levels of organization, which have an increasing distance from the detectable physical states on which it's ultimately all based, that it's not locatable in physical space, and it has a non-physical structure and function. This being the case, it may seem slightly odd that it's so easy for us to interact with computers if all of this really is hidden in some abstract, non-detectable information dimension. So how do we do that? Well, that's very simple, really, and that is because we have designed computers to operate in a particular way, we can use that design to actually deconstruct the bit coding which is stored on a disk or whatever, and reconstruct it in the form of, for instance, a pixel coding which we can present on a computer monitor. So we can actually, if you like, see into the information dimension of a computer, even though what we are seeing is quite obviously not actually what is there. I mean, the pixels you see on the screen are not the same as the bits on the computer disk, let alone on the information which is built from them. And considering this illusion of detectability, it struck me that, in fact, this is very similar to what we see in the brain. What is actually happening in the brain informationally is also completely inaccessible. Back to Chalmers, even if we were to actually map the entire connectome, all of the connections in between it, to know everything about the neurotransmitters, there is something there which you will not be able to find. And the only reason why we know that it's there, in another person in any case, I mean, obviously we experience our own inner world, but in another person, it's because they express it in some way. In this case, thinking about saying hello to somebody would lead to activity in the motor cortex, which would lead to activity in the vocal cords, which will cause somebody to actually express the word hello. And in that respect, you know what's been going on inside, but not because you can detect that, but because it has been converted into a physical form and expressed in some way. And as with computers, the topology and the space in which this happens is not the same as that which you see in physical reality. You see that even more so in neural networks, particularly small world neural networks, where distant nodes may be connected while close by nodes may not be connected. So again, here we see that distant nodes may be neighbors, and neighbors which are physically close by may be actually at a distance. And this leads to a completely different topology and a different space in the information dimension associated with the brain than with the physical substrates it's based on. And this is a sort of a simple network graph topology example of that on the left-hand side, you see a projection of a four-dimensional tesseract onto the two dimensions of this screen. What you see on the left-hand side is exactly the same. It's just that the position of the nodes have been randomized so that four-dimensional tesseract is still in there. It's just that we can't see it anymore because it doesn't match up with our dimensionality anymore. So again, here we see a similarity between technological systems and biological systems when it comes to how they deal with information and how it is separate from the physical. Something that I'll talk a bit gives this kind of picture that on both sides, what we see is that there is a physical space in which there are entities on which the basic units of this information structure are created, and that they are then constructed into sequential levels of organization, which on the one hand might lead to the functionality of a PowerPoint application, and on the other hand, the perception of a red rose. But all that happens not in the physical space, in the physical dimension, but in the information dimension, which is created from it. What we see then is ultimately only the top end of this, particularly in the case of the brain, whereas there are actually a number of underlying levels. In the case of the computer, those underlying levels are accessible to us because we know how they are built, because we've designed them that way. So as we saw before, we can actually decode them or recode them, reconstruct them on the basis of measurements of the bit states on which it's all based. On the brain side, unfortunately, we don't have a decoding mechanism that we can apply. So there, those intermediate levels remain invisible to us. And not only invisible from the outside, actually also invisible from the inside. And that is, in my view, one of the most important conclusions relative to consciousness, is that the fact that we don't see layers underneath that doesn't mean that they exist. They don't exist. It just means that we can't see them because we haven't any access to them. So going back to Chalmers' hard problem, as he formulates it, this is not quite what he said, but you can also say that even when we have explained the performance of all of the electronic processes taking place in the computer, there will still be an unanswered question: why and how is the performance of these functions accompanied by the PowerPoint software? And in the case of computers, actually, the answer is kind of trivial and simple. And the question why can be answered because we want them to do this. So we've designed them with this function. The question how they do it is also simple. We designed code-based systems on which we can program them and cause them to create the function we need. On the brain side, the why question is also fairly easy to answer. And that is, yeah, we are living organisms living in a complex world which requires responsive behavior. That responsive behavior is based on information which we extract from our environment and convert in our brains to actions which are directed at survival and success in that world. The how question is a little more complicated because that gets down to a very complex form of organic self-organization which takes place in the formation of function in the brain. So similarities and differences. Certainly what I'm not saying in this case is that PowerPoint software is aware or something. These different things in the information dimension have very different emergent properties, different characteristics. In the case of consciousness, we have qualia. In the case of PowerPoint, we have slideshows. Very different things, but all of them informational and high-level phenomena in this information dimension. So on the basis of this, I have a message for the philosophers, and that is, perhaps they will be disappointed, that consciousness is not unique or fundamental. It is actually sort of the top end of a stack of informational phenomena constructed from the initial fundamental elements of information created by neural activity. And it has a great number of friends and family in the information dimension. Even the PowerPoint presentation is in there with it. But there's also a message for the materialists, which will make Chalmers unhappy, and that is that there is indeed more to reality than the physical. And this is non-trivial. So that's much for the reasoning. How would this actually work? And this is something which I had trouble finding an answer to, but the answer that I finally came up with was that, in fact, every physical interaction that takes place creates this specific kind of information that I'm talking about. And again, it's difficult to actually use the word information in this context because it has so many different uses and connotations and whatever. And here, use of the word information may seem a bit strange, which is why actually, as I come to later, I prefer a different word for it. But for the sake of for how far we are in the talk at the moment, I'm using the word information. And that is that if, in this case, something causes the black circle to become white, then associated with that white state is actually information about what caused it. Kind of simple, but on the same level, it's also a bit odd. Why this is relevant is that, in fact, in all physical systems, this is completely irrelevant. It doesn't happen, but a physical system can do nothing else than respond on the basis of current state. If that white circle goes on to interact with another object in some way, then it is simply a white circle. There's no way that its previous events can influence what actually subsequently happens. And that is the fundamental difference with information systems, because in information systems, it is not the whiteness of the circle which counts. It's the information associated with it, which is imbued upon it by that which caused it. That is what actually causes the effect in the end. And a simple example of this, not the example yet, what this actually means is that basically everything in the universe that is a physical system works on the basis of the left-hand side. So there are interactions going on all the time. They are creating this associated information all the time, but nothing happens with it. So it's just a kind of a passive layer, if you like, over physical. The only systems that can do anything with this information functionally are systems that have evolved or been designed to exploit this information. And the example that I was just going to mention, very simple example, is the use of insulin as a messenger molecule in the body. What happens here is that if you have high blood sugar level that's detected in one part of the body, it leads to the release of insulin, which enters your bloodstream. The insulin goes somewhere else in your body where it causes sugar uptake. Now, the insulin molecule itself, physically, is totally uninteresting. What matters is that the receptor recognizes that the insulin molecule is associated with the information of high blood sugar. And that the conclusion of that is that it should do something to reduce that blood sugar. So here we see very much that distinction between the physical state and the information which is the function of that physical state. Now, in this case, you could say, so what? If there's a one-to-one relationship between insulin and the information it's associated with, then why be so difficult? Why insist that information, high blood sugar, is actually something real which exists in a separate dimension and deserves to be considered as something more than just an abstract property or whatever? As long as it's this simple, there isn't really much of a reason to do so. But as we've seen in computers, that's not actually how information systems generally work, certainly not brains and also not computers. Those binary values are useless to us. They're only useful once we actually go to that stacked layer of organization. And it's the stacked layers of organization which have the effect which we are interested in. And significantly, the combination of those binary values is done in the information dimension. There's actually no interaction whatsoever necessary in the physical dimension in order to have that take place. Those bits stored on a hard disk, they're just sitting there doing nothing, waiting to be read. It's actually the informational confirmation which creates the effect. So that leads to the conclusion, as far as I'm concerned, that in fact, while we have physical entities with physical properties on the one hand, we also have informational entities with informational properties on the other side, and that is what really matters. And that makes emergent information theory a fundamentally a substance dualistic theory. According to this theory, it's not sufficient to think about these informational entities just as abstract properties or whatever. They deserve and need to be considered as entities in their own right, because it's there and their properties which lead to the creation of these higher levels of organization. So on that basis, we could say that certainly in the case of the computer, the indivisible unit for the construction of these higher levels is the binary value. In the case of biological neural networks, it's a bit more complicated. That may well be the synapse, it could be a neurotransmitter, it could be a neuronal state. But in any case, at some level, there is an interaction which causes the creation of this information, which is the basis for the construction of those higher levels. With these being fundamental units, I consider it appropriate to consider them as information quarks, you could say, or I-quarks, you could also say. And the term which I kind of struggled with, because it sounds a bit tongue-in-cheek, is quirk. Until I realized that, in fact, these things are rather quirky, in the sense that they're so very different than anything which we're used to thinking about as a particle or as an entity. And it's on that basis that, as I say, emergent information theory is substance dualistic, in which we need to make a distinction between the historical substance dualism, Cartesian dualism, which is in the same line, you could say, but basically consciousness in the context of emergent information theory is only one example of this dualism. it's only the tip of the iceberg in the brain, and it is certainly not unique in that sense, because all information technologies also have and operate on the basis of this substance dualism. This brings me back perhaps to the Information Physics Institute. Information physics is certainly also something which could be used, have many different interpretations, which I've also seen in some of the talks which I've had a look at on the website. But information in the way that I'm using it also has a physics, in the sense that there are various processes and interactions and combinations between these component parts taking place in the information dimension. And they will certainly also have their own physics. I mean, not material physics, but informational physics. That is necessary because if there wasn't a rule-based system here, they wouldn't be able to operate in a consistent way that is necessary to ultimately create these higher level processes and phenomena. So, wrapping that up, what we can see is that there's a great diversity built on the basis of these fundamental units of information which are created by, on the one hand, digital systems, and on the other hand, neurological systems. In computers, that could be anything from a PowerPoint presentation to a photo of a digital photo of a Christmas tree. It could be a text document. It could be a relational database, as we saw earlier. A great diversity of different things which can exist in the information dimension of computers. On the human side of things, everything from emotions to phenomenal consciousness to the plans that we make for the future, even something as crazy as emergent information theory. Those are all things which exist in the diversity of high-level phenomena created in the information dimension of the brain. And of course, on the brain side, there's also another big chunk on this side, which, as I mentioned before, is unfortunately inaccessible to us both in our own minds, but also certainly in the minds of others. And that is the subconscious, because that is just not accessible, in spite of the fact that it definitely is there, because we see a lot of effects of that, apart from the fact that we need it basically to bridge the massive gap between any information that could be associated with individual neuronal states and something with the complexity that we see in these examples. That's basically my story, and my story has a number of consequences, which a large number of consequences, in fact, but a few of them I'd like to share with you. And this is the first one, which I've tried to depict in this way, and that is the relationship between our perception of our surroundings and those surroundings themselves. What you see here, or what I'm trying to bring into view, is the fact that if you're walking down a street, you see things around you. You see trees, buildings, benches, and whatever. But what you're actually seeing, what you're actually perceiving, is not that outside world. What you're seeing is the reconstruction of it within your own information dimension. Obviously, that is based on, or at least my take on that is that it's based on the photons which are entering your eyes, reflected off those objects in the outside world. But the tree, for instance, in the outside world is not green. The tree just happens to reflect wavelengths of light of a particular frequency. The greenness is, as Chalmers would say, that is a qualia. That is something which only exists within your own mind, within your own information dimension. So when you're walking down the street next time, look around you and realize that everything which you are seeing is inside your own information dimension. One of the objections when I first thought that myself, I thought, but how is it possible? How could something so big, something which I perceive in any case is so big, how could that fit within the 1.5 liters of my brain? And the answer to that, of course, is that it doesn't fit in the 1.5 liters of my brain. It fits in my information dimension. And one of the characteristics of a highly convoluted network is that it has a higher level of dimensionality. As we saw in a previous slide, a 4-dimensional cube can very easily be represented in a neural network. In fact, a 20-dimensional cube could be. There is absolutely no limit to the number of dimensions that can be created in a neural network. And that creates enough space for all of that to fit inside your information dimension, which is created by that 1.5 liters up here. What are the consequences? Another one which is worth mentioning is the fact that it doesn't stop at the level of the individual human. What I'm now doing, talking to you over the internet, whatever else, I'm communicating information. So information is traveling from my information dimension into your information dimension. That's what we do every day, every moment of every day. Wonderful thing about language. And this is an example of things which can take place at a higher level of organization in the information dimension, is self-organizing echo chambers in social media. There are interactions going on between individual humans, and obviously that is mediated by the computers or the smartphones or whatever they're using. But what is actually happening is that information is being transferred between information dimensions, and that a network is being created in that way, which has properties of its own, which could not exist in any individual information dimension. So that's one example. And of course, what I just mentioned, technology is also a part of that. We work together with our computers and in networks of computers, networks of people, in which the function of the whole is also more than the function of the part. And that function actually all exists. It's combined in the information dimension, not in the physical dimension, in spite of the fact that we mediate it through the use of keyboards and monitors and that sort of stuff. And that also applies, the bottom picture here, you could think of it as an organization, for instance. Organizations these days sometimes have physical products like the cars we were talking about, but a lot of organizations actually only have informational products. A bank, for instance, these days doesn't produce anything physical. It's only involved with information in the form of money or whatever else it may be. And all of that, in spite of the fact there may be a bank building somewhere where people go to, or perhaps they're working from home, working on the computers, the complete sum of what a bank does exists, in my view, in the information dimension. To wrap this all up in 4 slides, what I'm claiming is that materialism, as Chalmers says, is indeed incomplete, because every physical interaction creates a quirk, and that is a fundamental unit of information about the cause of the interaction, which is carried by the subject, if you like, of that interaction. What I'm claiming is that systems have evolved and been designed to exploit these quirks. And they're very different than all of the physical mechanisms, the physical machines, which have also been created. They do this by combining these quirks into stacked layers of organization with emergent features. And this all takes place in an information dimension that is created by each information system. So you could say that we're kind of looking at the 3 dimensions around us now. It's kind of a flatlander's perspective of the whole of reality, because these information dimensions obviously don't fit into our 3-dimensional space and time. They are a kind of a parallel dimension, or a connected parallel dimension in any case, which is created and which has a volume of its own in which all of these things take place. So that is my story. And I'm very curious as to what everybody thinks about it. So I just